Today we have Cherry speaking on ROG-graded cohomology for the nonabelian group of order 21.
Hi everyone, thanks for coming. Just a caveat, this is my first time giving a slide talk, so thank you for your patience and please bear with me through any minor mishaps. Also, I don't really know how slides work for timing. Someone was like, 15 slides is so little, and someone else said, that's so many. So I'm gonna try my best, and if I run over, feel free to cut me off. Okay, so here's what I plan to talk about. I plan to discuss a little bit about what I mean when I say ROG-graded cohomology. And then I plan to review some computations that have already been done. And then I plan to talk about computations for the non-abelian group of order 21. So what do I mean by ROG-graded cohomology? It is a cohomology theory for spaces that come with a group action. It is the fullest or best generalization of singular cohomology for spaces with a group action. And here are some nice features. It is stable. I'm going to go more into that later. I haven't really described what that means. It is proven to be useful, for example, in the Crevert invariant 1 problem by Hill, Hopkins, and Ravenel. They extend some ROG-graded cohomology computations and then use the periodicity to prove the important result, the Crevert invariant 1 result. And I also, in like something, I don't know if this is less famous, but I also came across a paper while I was poking around prepping for this talk where ROG-graded cohomology was used to access just the Z-graded part of the cohomology in order to prove something, the Connor conjecture. I don't know anything about it. I just read like what it said. Okay. Also, it has really powerful splitting theorem and the same, and it like gives orientation to G bundles. Okay. So while I want to talk about in what sense I mean that ROG-graded cohomology is stable, so I'm going to take an aside and talk about representation spheres. So the definition of real representation that I'm going to use here is a group action of G on a vector space Rn. I know there's another more popular standard definition, but I hope that we can agree that this is equivalent and that the geometric perspective is useful for what I'm about to say. A representation sphere is an n-sphere with a group action where you take the Rn that you just put a group action on and you do a one-point compactification and turn it into a sphere. I'm going to do an example in a minute. Okay. So just as a quick example, if your group is C2 and your vector space is R1, then the group acts on the vector space by taking 1 and mapping it to -1. This is the sign representation. And so a picture of this would be, here is the real line, and that's 0, and the group action swaps the left and right sides. Now if we take this R1 and we compactify, is the handwriting legible to people? I don't know how to look at
Yes, looks good.
Okay, thanks for the thumbs up. That's helpful. All right. And so if we compactify, then we will get a copy of S1 with the point at infinity at the top, 0 at the bottom, and now the left and right sides of the circle flip with each other. And so this is an S1 with group action. This is a representation sphere for the sign representation. Cool. Now let's do another example. If your group is C7, by C7 I mean the cyclic group of order 7. I should have said that when I said C2. Maybe I didn't say C2. And the vector space we'll be using is R2. And so the representation is going to be multiplication by e to the 2 pi I over 7. I know I'm cheating by using complex numbers, even though we're in R, but hopefully you understand what I mean. I mean rotation by 1/7 of the plane. So I'm going to draw a picture of what happens to the vector space. Here's a picture of R2. And here are, oh no, I have to draw a 7 star. That's bad. All right, that's better than it was in practice, so I'll take it. And it rotates, the generator of the group C7 rotates by 2 pi over 7. Then, if we do the compactify, lost a letter, that's okay. Then we will get a copy of S2 that looks like one, two, three, four, five. Whoops. 6, 7. Looks like an orange. And the action of the group is to rotate this sphere. All right. As a bonus, let's also talk about what happens when the representation is a direct sum. So again, we're going to use the group C2. And so if this, we're going to use the same representation on the left here, the top one, where the vector space for V is 1 copy of R. And so the vector space for V, direct sum V, will be R2, where the action is to take one axis and flip it, and also to take the other axis and flip that. And if we compactify, then we will get, well, this is going to be hard to draw for me. Sphere where you have a front half and a back half, and you rotate by 180 degrees. So these are all examples of representation spheres, spheres with a group action by the group G. Okay. Let's see. And so now we're ready to talk about what we mean when we say that ROG graded cohomology is stable. So here is a comparison of ROG graded cohomology with singular cohomology. So for singular cohomology, you have an ordinary space. For ROG graded cohomology, the space has a group action on it. For singular cohomology, the spheres that you're interested in are the ordinary spheres SN that you're familiar with. But in ROG graded cohomology, instead of working with spheres with no action, we work with representation spheres. And the reason is because if you take a sphere with no action and suspend or like smash with that sphere, you will fail to capture, like it doesn't have a group action on it, right? It will not be interesting in the eyes of this cohomology theory that detects group action. Okay, the other thing is the suspension isomorphism is different. So in singular cohomology, you may have seen this before, and the nth homology of a space is the same as boosting the degree of the homology by K and also smashing with a K sphere. And so you may think of this as like the K's cancel. Don't say that. In ROG graded cohomology, there's a similar property where the boosting the cohomology by a particular representation is the same as smashing with that representation sphere. And so they cancel in that same way. And so it is in this way that I mean that singular cohomology is Z-graded, that these numbers here live in the integers, and the cohomology theory that I'm talking about here is ROG graded. In other words, it is the ring of representations that is the grading on the cohomology. another important difference that I'm going to use these two facts later, that's why I'm mentioning them now, it has nothing to do with the stability that we've been discussing, is that singular cohomology is made of abelian groups. That when you compute singular cohomology, you get a bunch of abelian groups. ROG-graded cohomology, because the group that you're using that has to do the action has subgroup structure, instead of just getting one abelian group, you get a diagram of abelian groups. So this is what I mean when I say Mackey functor. There's a lot to go into here, but I'm just going to call this a diagram of abelian groups. And the diagram of abelian groups is in the shape of the subgroups of the group that's performing the action. And so the idea is that it is a diagram of abelian groups that is capturing not only the cohomology that we wanted, but also something about the cohomology that is created by the action by subgroups and also the fixed point groups by the subgroups. Okay, and the last point is in singular cohomology, the reduced cohomology of a point is not that interesting. It is, 0 all the way up. But in ROG-graded cohomology, because of this suspension isomorphism, you can compute the cohomology of a point by considering the cohomology of the representation spheres. And so you may be wondering, why would I want to do spheres instead of a point? That seems more complicated, not less complicated. And I think the way that I think about it is that the spheres have convenient properties for computation that make it better to compute on this side. And I'll show you some examples of that later. So back to this slide that talks about what are the properties of ROG-graded cohomology. Oh, another property that's good to know in case you venture into this field is that there is a Z-graded cohomology that is called Bredan cohomology. And ROG-graded cohomology is sometimes also called Bredan cohomology. So it's kind of confusing. You'll have to figure it out from context. I feel like I struggled a lot with this in the beginning, so just should you read about it, there's some like double use of that term. Okay, so we talked about in what sense this cohomology theory is stable. We already talked about these. Awesome. And then one more bullet point, unfortunately, it's really hard to compute. And that is very sad. All right. I'm going to pause for questions and comments. Looking at my progress through this, I'm like 6 through my 15 slides, so please do ask questions if you have them, because it is very much my intention for you to understand. And also, I'm a significant way through the number of slides. Oh, there's something going on in the chat. Handwriting is legible. Okay, that's a different thing. Are there any comments or questions? Okay, I will continue then. All right, so even though the computations are hard, we must not lose hope. And I'm going to talk about some computations that have already been completed. For people who are familiar with this field, I am kind of sweeping under the rug what coefficient system is chosen, like I'm just not mentioning it. Some of these computations are done with constant Mackey functors, and some of them are done with the Burnside ring Mackey functor, but I'm just not going to talk about it. Okay. So in 1988, there was a paper by Lewis where the appendix includes unpublished work by Stong, and in it, Stong computes the cohomology of a point for the groups C2 and C3 for the cyclic groups. All right. Then in 2004, there is a paper that computes the cohomology of a point using for the group CP, where P is a prime, for cyclic groups of order P. And it uses a very special property of CP to conclude that a lot of the diagrams of abelian groups are the same. And so in order to avoid doing computations, there was a lot of like saying, oh, these things are the same, I'm going to do this other computation instead, and used a lot of that kind of trickery. And then in 2015, there were computations completed for the group Z mod 2 to the n. And in it, the author claims that they chose to focus on this group because the representation ring of Z mod 2 to the n is particularly nice. And what do they mean by particularly nice? All of the real representations are one-dimensional. And they're basically all the same. They're not isomorphic representations, but it's like pretty much all the same. And so the representation ring is super, super convenient. And then just 2 days ago, I saw a paper. It didn't come out 2 days ago. That's when I saw it. That computes the cohomology of a point for the permutation group S3. And they do it by explicitly constructing an equivariant CW structure on the sphere. So like they treat S3 as, you know, like S3 also lives a double life as a dihedral group, as the symmetries of a triangle. And so they treated, oh, that's not a good triangle, is it? Oh, that's a fine triangle. And they treated the triangle as living in the plane, and they kind of cut up the plane according to the symmetries of how you would like, how the group action would flip the triangle back and forth. They cut it up into little pieces, and then they computed the cohomology like as if you were doing that simplicial homology exercise that you did way back when, where you like take boundary maps and you have like alternating sums of like the kind of classic method where you can like really get hands-on and just do it with an explicit structure. And since S3 is a dihedral group in disguise, they were able to extend this method for all dihedral groups. And this is the first one that I've seen that is for a non-abelian group. There's also, like I mentioned before, maybe I can jot it down here, in that Hill-Hawkins-Ravenel paper, Curvaire invariant 1, they also extend the computations for Z mod P to the n. But I ran out of space on this slide, so I just squeezed it in right there. And the takeaway from looking at all these computations that have been completed are that, number one, they're pretty hard to do. And number two, the ones that are complete tend to be for a lot of cyclic groups. The ones that are not for cyclic groups have some nice property to them. For example, that S3 has at most a two-dimensional real representation so that you can draw it and physically cut it up into little pieces. And the same with all the dihedral groups. That dihedral groups may be non-abelian, but their top dimensional real representation is degree 2. And so you can draw the picture and cut it up in a really sensible way that makes it really amenable for computations. Some other computations that were done is earlier this summer, my advisor ran a research experience for first-year graduate students at my university. And we do it every year for all the first years. And they did basically this kind of computation, but they wanted to extend the space of interest, not just to representation spheres, but to representation spheres that have been projectivized. So let me say more about that. In particular, they were working with the group C4, the cyclic group of order 4. It has representations, sigma, which is a one-dimensional sign representation. That's the one where you have a copy of R and you flip the left sides back and forth. And then they also have lambda, a two-dimensional representation. And this one is the one where you rotate the plane by pi over 2. 2 pi over 4, pi over 2, yeah, okay. And then inside of that vector space, they take the unit sphere, and then after that, it projectivize, and they're interested in the cohomology of that space. And so let me give you an example. So one of the pieces that they worked with was this representation that, I guess I mean O plus, I should have written O plus. And what I mean when I say 1 plus 2 sigma is one copy of a trivial representation and 2 copies of the sign representation. And so this is 3-dimensional. And I will draw you a picture of it. I've been working on my 3D drawing skills because I'm anticipating teaching Calc 3 in the fall. So, oh, that's really good for me. Excellent. All right. So one copy of the trivial representation, let's pretend that that copy lives on the vertical axis. So this one is still. And then 2 copies of the sign representation. Like that example we did before, when you have 2 copies of the sign representation in R2, what you end up with is a rotation by 180. And so this rotates the plane by 180. So inside this, you take the unit sphere. What does that look like? It's R2. So here's R2. And the unit sphere inside this R3, because the action is to rotate all of R3 by 180 degrees about the vertical axis, this sphere is also going to rotate front to back. And then the last step is to projectivize, and I'm not going to draw this because there's really no hope for it, but the idea is that a generic point X, Y, and Z under the group action would have mapped to negative X, negative Y, Z, and then under the projective identification is X, negative Z, for example. And so they were able to draw a picture of this. I can't draw a picture of it. If I could have convinced them to come, they would have drawn a picture of it, but they're busy studying for prelims right now. So they were able to cut it up into little pieces and do the computations. Unfortunately, I wasn't able to find their final answer. I'm kind of disappointed in that, but it's somewhere. And if you are interested, we can talk about it, and I am sure I will find it eventually. Okay. Thoughts and comments so far? All right. So, given these computations that have been done, it looks like perhaps there is hope for doing future computations. And that is where we start this next part. So a little bit of background about the nonabelian group of order 21. It is the semi-direct product of cyclic groups. In this case, it is C7 semi-direct C3. And it has 2 representations. It has 2 representations, and we're going to talk about them one at a time. The first one is a 2-dimensional real representation that I'm going to call small lambda, and the other one is a 6-dimensional real representation that I will call big lambda. The 2-dimensional representation, small lambda, is formed by taking, oh, I forgot to give the other definition of a representation. Okay, the other definition of a representation. Oh, also this is wrong. That should say GL2R is it's a group homomorphism from G to GL and R. That's the other definition. And so we can form this small lambda by taking our group, and the first map is the quotient by the normal subgroup C7. And then the second map is the rotation by 2 pi over 3 representation, where C3 is mapped to matrices that rotate R2 by 2 pi over 3. That's the action. And so this representation is basically already covered in the known computations. This representation, that's rotation by 2 pi over 3, is already covered in the literature. And if you compute the cohomology of a point for this representation, you will recover the same answer that you would have gotten if you had been working with C3 all along and just kind of ignoring this part. The fact that it came from the group of order 21. And I'm going to draw it for you the first time just so you can see what I mean by a diagram of abelian groups. So in degree 2, you will get and the label on these maps means multiplication by that number. So 1 is just the identity map. And this is 1, 1. And all the other maps are 0. And for n not equals 0 or 2, these are all 0. Okay, so this is the first time that we've talked about an actual result. The cohomology is, as promised, a diagram of abelian groups, and it is in the shape of the subgroup structure of the group in question, C7, semi-direct C3. I am suppressing for those of you who immediately are, excuse me, what about the other groups? Yes, there are more subgroups than just C7 and C3, but they're all conjugate to each other, and so I've just kind of suppressed them. If I were to draw it for real, it would look like kind of unwieldy, and so I've just suppressed them because they are conjugate. And so this result is not remarkable. It is the same as it would have been for C3. Next. Turn the page. Okay. So for big lambda, the big representation, big lambda, can be built from a two-dimensional representation of the subgroup C7. So what do I mean by this? Take your vector space to be R2 and take the two-dimensional representation of C7 given by rotating the plane by 2 pi over 7. So like what we said before, it's rotate by this much, and if you were to compactify, you would get 2, 3, 4, 5, 6, 7. It's not as nice as the last one, the sphere. Then big lambda is the induced representation where you tensor up over the group ring from the group ring of the subgroup to the group ring of the whole group. And so if that's not intuitive to you, that's okay. I can draw a picture about what that means. So in essence, this means that there are 3 copies, too big, of this 7-panel beach ball. By the way, while working on this, I realized most beach balls have 6 panels. So where the action of C7, okay, is to rotate this, and same on all the other spheres. The action of C7 is to rotate those spheres, and then the action of C3 is to shuffle the spheres amongst each other. And so there's some back and forth between the spheres going on. And I know it looks like it exists in R3. It doesn't. This lives in R6. But you can think of taking these 2 spheres and smashing them together to get a 6th sphere. And that is the representation sphere of big lambda that we are concerned about. So if we were to smash together, we'd get S big lambda. All right, so at this point, recall that earlier we talked about the completed calculations. All of the groups with completed calculations had representations of dimension at most 2. And so we can already see that this problem is going to work a little differently because 6 is a lot bigger than 2 and really hard for me to draw. So what I have been working on is taking the cell structure that you get from the 7-panel beach ball and smashing it together with 2 other copies of itself and trying to find an orderly way to get an explicit GCW cell structure on the 6th sphere, and then do the computations explicitly the old-fashioned way, like what I described, where like you delete the vertices one by one and you do an alternating sum of, you make the boundary map in this way. And here is the result so far. So what we have is that it is concentrated in even dimensions. There are still some unknowns, as you can see. We are not done, but that is something that I hope to finish in the next, I don't know, month or so, all like virus willing. And questions or comments at this point?
I'm curious what techniques you're using to compute these.
Can you say a little more?
So are you using like long exact sequences or?
So far, no. So far it is gosh, I don't even know how to describe it. It's like so explicit. It is like
are you doing very manual, like cellular sorts of computations?
I would say it has a flavor of simplicial type computation. Okay. You're like really writing down a simplex in terms of its vertices, and then you like delete the vertices one by one and get that alternating sum boundary map.
Okay, and then do these simplices have group actions on them as well?
Yes, they do.
Okay.
So part of the challenge is that the simplices have to be not just CW cells, but they have to be GCW cells, and so there's like some fussiness about like whether the group action, like, does it take a simplex and turn it and map it to itself? If so, that's like really bad. But if it takes a simplex and like under the group action moves it to a whole new simplex, that's really good. And the geometry has been really challenging because visualizing things in 6 dimensions is way beyond my puny human brain capacity. So it's been like an exercise in like trying to abstract things way beyond what I can visualize, and that's been part of the challenge.
Okay, cool. Yeah, I think I'd like to hear a little bit more about these simplicial techniques maybe another time, but thanks.
Yeah, cool. And I think the hope for the future is that this method seems pretty straightforwardly generalizable to non-abelian groups of order PQ. You will have a non-abelian group of order PQ whenever P is like 1 mod Q or something like that. And also the next steps after this computation are to look at confirming the computation through other methods. So we're thinking either looking at doing the same thing through the slice spectral sequence, or maybe through isotropy separation, or a bunch of other less directly computational methods, just to feel good about the results, because this is like a huge mess of matrices and hand computations and computer computations, and it's like not the most comfortable way of arriving at the result. And so the plan after this is to confirm with the choice of other methods. Are there any questions or comments at this point? Okay, well, given that I've never given a slide talk, I have like severely mistimed this. Sorry, I'm a little bit short and I have come to the end of the material. So I guess like if we wanted to have like a more informal part where people just kind of like, you know, look over things, what's this, what's that, I would be happy to do that. Otherwise, I'm gonna let the host decide what we should do.
Yeah. Well, first, on behalf of everyone, I would like to thank Cherry for speaking. Are there any further questions for the recorded portion of the talk?
I guess, so first of all, this is a cool talk, so thank you. And then I had two questions. So first is, I'm sorry if you already said this, are the computations you just showed, is that the constant Mackey functor Z, or is it a different one?
This is for the constant Mackey functor Z. Yeah.
Okay, awesome. Oh, sorry.
Mm-hmm. Did you have a second question?
Oh, yes. So is there a reason that you picked this this group of order 21 rather than, there's also there's other interesting semi-direct products that are smaller, like C4 and C3, or C3 and C5.
Mm-hmm.
And so my naive guess would be, because they're smaller, they're easier. But maybe that's wrong, / like, you know, what about this group in particular made it the right thing to compute?
What were the other groups that you mentioned?
So there's one of order 12.
Yeah.
Which is either C4 semi-direct C3 or C3 semi-direct C4. And I don't remember which of the two.
Yeah.
And
and the other one?
I think is there one of order 15?
I don't.
3 and 5?
I don't.
Okay.
Think so.
Okay.
So the way that I came across this group is my advisor first mentioned when I first started this project. She said, I want you to do these computations for the Klein 4 group. And we were like 2 months into looking into it, and she goes, never mind, somebody else's student is already a good way into that. We need a different group. And she had a conversation with Doug Ravenel, and this was what he suggested. And so like I didn't really have any notion of what would be a good group to pick at that point, and this was totally like Doug's urging in this direction. I think he probably saw that it was like generalizable, but I think that, you know, I should look into this. See, wait, is there really a non-abelian group of order 12?
Well, there's a couple.
Yeah, but it's not
right? Like,
C3 semi-direct C4, right?
uh-oh.
Well, maybe.
I thought it was.
Okay.
I mean,
I'll think about it.
Well, there are a couple non-abelian groups of order 12. So D6
Yeah.
and A4, and then there's one more.
Yeah.
Okay.
Okay, that's I should think about that. I'm not certain.
Let me go look it up right now, actually, to make sure that I'm not misremembering. I'll be right
I'm
back.
sure you're right. I think it's probably just because 4 isn't prime. And so he wanted something with 2 primes, something kind of manageable. You know, like 4 is a P group and sometimes can get a little unwieldy and have some heavy structure. Are there other things that people want to discuss while we reference?
I was wondering if you ever ran into, I suppose for this computation, you wouldn't have ever been looking at the product of your G simplices.
What do you mean by the product of the simplices?
So like non-equivariantly, if you're going to, you can take the product of them and then have a map from the product, like a map out the product. But that, I don't know, one thing I ran into recently was looking at like constructing an explicit map from the product of two G simplices. And that was challenging because how do you nicely subdivide something with a G structure on it? So, yeah.
I would say that
you probably did not run into that at all.
It came up in this step where, so this 7-panel beach ball was divided into simplices that look like, you know, wedges. And when you tensor up, you are taking the direct sum of 3 copies. And so in the sphere world, that would be like smashing the 3 spheres together. And so the way that I came up with that structure was like to use the product that's the first step in the smash product, where like you smash and then identify. And so it was like the cell structure that I came up with for big lambda is made of cells of this form times itself 3 times, like the product. But I agree with your assessment that like finding an equivariant way to divide it was like the major part of the challenge.
Yeah, that certainly makes sense. All right, any other questions? Okay, I'll go ahead and end the recording.